Hello, everyone. Thank you for joining our large scale simulation and design optimization TTA. And here, this is my honor to actually introduce Professor Alicia Kim. And her talk, as I was discussing before starting the recording, is very related to our talk. And the title is very short. I love those kind of the title. So large scale topology optimization. But first, allow me to, in a few minutes, I introduce Dr. Kim. Dr. Alicia Kim is a professor in the Department of Structural Engineering and Program for Material Science and Engineering at the University of California, San Diego. She has several affiliated appointment with mechanical and aerospace engineering and electrical computer engineering at the same university. She is director of M2DO, multi-scale multiphysics design optimization, where her people and a student and postdoc, they are developing topology optimization and computational methods for multiphysics, multifunctional system. And the application are spanning from aerospace, energy storage, and additive manufacturing. She also leads two centers funded by DOE. One is an NNSA PSAAP IV shape. It's called for simulation and design of heterogeneous architecture for performance and energy absorption. And the other one, DREAM Center, dynamically responsive emergent architected material system. And in these two projects, they are working on multi-scale nonlinear material design with DOE labs. She's author of over 100 peer-reviewed journals in the field of topology and material design, multi-scale, multiphysics, and computational mechanics. Professor Kim has served on editorial board of several journals, including Structural and Multidisciplinary Optimization, that it is our main society journal for ISMO, and has been actively engaging with research community on executive committee for International Society of Structural and Multidisciplinary Optimization, AIAA, MDOTC, and US National Congress on Computational Mechanics. With this introduction, so Alicia, floor is yours, and you can go ahead. So thank you.
Thank you very much, Ahmed, for that lovely introduction. Very kind. And thank you again for inviting me to give this talk. What I'm going to do is since this is a large scale TTA that wanted to look at what we mean by large scale and where we need more research in topology with the topology optimization in mind. So I hope I'll be able to sort of give you where we're going. So how I'm looking at large scale topology optimization, I sort of summarize in these three categories. So multiphysics, multidisciplinary, and multi-scale. I see that as one category because essentially the way that we think about multiphysics is that if there is more than one governing equations. So multi-scale becomes essentially if the lower scale has a different governing equation, it just becomes a different scale problem. Or even if the lower scale may have continuum, homogenization acts as sort of like the coupling physics. So in a way, we see a lot of the mathematical computational tools that is required in this field is more or less very similar. So I categorize that as one category where essentially you have multiple governing equations, potentially multiple domains, and then how we actually couple these things both in terms of physics and also in terms of discretization. Now, so those are sort of one class of method that we talk about, and then there is the sort of a classic, what we immediately think of as large scale, which is that basically we have lots and lots of elements. And here we're going to talk about some of the approaches that we were able to enable using sparse grid. So essentially the idea is sort of like adaptive grid in that you want finer meshes where you're needed. And then you don't have so many further away, but we actually then link that to the memory structure. So the actual memory footprint reduces. And as a result of it, compute resources can be very efficiently used. So I will talk a little bit about how some of the things that we've been thinking about in terms of approaching large scale here. And then the third category that I'm going to talk about is topology optimization with uncertainty. So basically, this is the class of method that when you have the outer loop as topology optimization and inner loop that does the simulation or modeling, then there's a middle loop which needs to do the uncertainty quantification. And topology optimization traditionally is considered a very large scale problem compared to some of the UQ style techniques that have been developed. A lot of the standard UQ techniques don't apply directly, and a lot of the work has been how do you do the middle loop in the most efficient way possible. And by doing that, I guess we sort of think we kind of think that Monte Carlo is out of out of bounds. We don't think that Monte Carlo type techniques is applicable. So basically, it is all about how do we do that middle loop in such a way that we can do an effective calculations. And you can sort of think of that middle loop as a nonlinear calculation, explicit transient calculations and things as well. So although I sort of named it topology optimization uncertainty, under uncertainty, I'm talking about essentially how do we add a middle loop that is not very that requires more than sort of 5-6 iterations. So those are the sort of three classes of the topology optimization that I'm considering large scale, and I'm going to sort of go through a few examples of the kind of things that we've done in these areas. So one of the things I think is important to identify, although hang on, I'm just going to see if I can hide these things. Okay, so one of the things I think is a critical enabler is to develop this modular software architecture. So here, what we consider as generalized interoperable architecture for topology optimization. So essentially, what we're doing here is to decouple topology optimization to finite element method. So if the finite element method happens to be the choice of discretization and techniques that you want to use, and so you want to use something more like SIMP, density-based approaches, then essentially this mapping procedure, which maps the mesh design grid to the analysis mesh, this mapping is just one-to-one. So standard density base obviously fits in here. For those of you who might know some of the work that I've been doing more recently, we've been doing a lot of level set based topology optimization. So in our case, we have the design update that's happening in the level set and using the level set grid. And then we do the mapping between the level set grid to the finite element solve or some kind of PDE solve. And as long as your PDE solve gives out some sort of partial derivatives that allows us to map it onto the design grid, we can actually generalize this framework. One of the important things that this enables us to do is that we can then start using any PDE solver, and also those that are existing software, as long as there is a way that we can output the partial derivatives. So with this modular architecture that we have built, we are able to actually we've actually demonstrated this work flow using MATLAB to console to commercial software, and also we have in-house software available and things like that. So from then on, we are able to build, for example, a more complex multiphysics workflow. So here is a fluid structure interaction. You can see my blue mapping, light blue mapping is here. So here, what we're doing is we're using the level set grid, which is the green side is the level set design update. And what we do here is that we have a the standard regular grid that we use for the level set optimization. And we actually, our level set method, the most recent version now, linearize the optimization problem, and we generally solve simplex optimization, which then determines the velocity to solve the level set advection equation. So all of those are the bit that sort of updates the design. And then we've got this blue mapping that maps the grid, the design grid, level set grid, to the analysis grid. Now, the analysis grid that we have for flow structure interaction is that we have this Eulerian background mesh for the fluids. And then for structures, we actually use RKPM, reproducing kernel particle method. And we've done quite a bit of work using this RKPM for solids calculations. Obviously, we don't have mesh deformation problem. We move the particles directly where the boundary conditions are, so we can apply more accurate boundary conditions. There's quite a lot of benefits that we can gain, but also fundamentally, RKPM is a higher order method compared to something like traditional finite element method. So using higher order interpolation, we don't actually have to use any filtering or any regularization, and the sensitivities are much more accurate. We can get faster convergence. So in this case, we've got two grids that going into fluid structure interaction. One is RKPM, the other one is fluids. So now then we can use our standard fluids type solver. We've actually used a finite element to solve this, but there is really no real reason to have to use finite element. Also, the orange color represents where the RKPM sits, and so we have the mesh-free technique. So we can actually build up this workflow approach to flow structure interaction. And then as long as it passes out the couple sensitivities, we can then just move on with our standard level set method without actually having to change any optimization software. So we do this, and we're going to demonstrate just very quickly. This is a problem from Kurt Mauty's group, 2016, that did this flow structure interaction. What is notable about this particular benchmarking problem is that the both objective function and constraints are on fluid-based criteria, and what we are actually changing is just the mechanics. So it's a really good demonstration of couple multiphysics problems. So they did this work, and this is the optimization results that they have, and they use linear elastic. So what we added, fluid structure interaction, but also that geometric nonlinearity. So when I was talking about topology optimization under uncertainty, the fundamental problem there is to add the middle loop. Geometric uncertainty is a case where you have the middle loop. And here we're using the particle method. So you can see that there are many more particles along the interface where we're calculating the levels, sensitivities that we map onto our level set. And essentially further away from that level set interface, we have very few points and particles. So you can sort of see how the design changes as a result of this optimization. And when we compared the nonlinear optimum versus linear optimum, you can see that on the left-hand side is the pressure distribution of linear elastic designs optimization that use linear elasticity. And then we did the nonlinear calculations to see how the linearly optimized design performs in this flow versus a non-linearly designed flow. And if you and the picture below is superimposing those two. So you can see clearly there is a different way that these two geometries actually behave as a valve, and there's 12% improvement in terms of actually considering nonlinearity directly. So we find that in some applications at least, that we can get very different design if we consider nonlinearity in structures. So this is another class of problem where we are doing some work. We have been doing a little bit of work in this nonlinear dynamics metamaterials. So essentially, these are type of materials where if you have nonlinearity in the material, so let's say in this blue blue lines or the sort of beams that you have, that is a piece of material and it's made up of some nonlinear and some linear material. So that linear to nonlinear it has the same linearity, but had an additional nonlinearity. And we've done some normalization so we can consider those two things to be equivalent. And when we do that, and we have this pink ball that hits one end of it, you can see clearly, as you would expect, the kinetic energy travels all the way to the end and back, and it just goes back and forth. That's exactly what you would expect. But what you would see on the bottom one, which has some linearities that tailored the properties, that you can see that this kinetic energy sort of goes somewhere in the middle and then it disappears. So if you are standing on the other side of the pink ball, then if that material between the pink ball and you is linear, you're going to feel that kinetic energy. Whereas if you have the nonlinear material, you're not actually going to know that pink ball hit it. So there are ways that we can manipulate the way that kinetic energy is transferred and how the wave transfers inside the material. So that's sort of the studies that we're trying to do. So this is again looking at very highly nonlinear design. So you can see from the experiment kind of sort of quite an aggressive, violent reaction of the material. So what we want to do is that we want to design what this inside of the blue material should look like in order to be able to achieve this kind of nonlinearity that we're after. So here is a recent paper that actually introduced some of those ideas. So how we actually approached it, and this was one of the outcomes of our Center for Dreams, where in the diagram A, we have a lower scale optimization using discrete element model. So essentially, we are designing the stiffness, what the stiffness distribution through the blue material should look like. So we do an optimization in such a way how the dynamics need to be that minimizes the kinetic energy that travels to the other side. So we get a series of stiffness, nonlinearity that we need to optimize for. So in this section B is the next level topology optimization, where the box A has given this kind of nonlinearity that we need to achieve. Yes. So then we can do that optimization, which is in C. You can see that the target fit outcome of the section A was blue, and then the optimized version is this nonlinearity in section red, in the line red, and you can see that it actually needs to match really quite accurately, and this is what we are actually getting, and we demonstrated that how that works into the experiments. So we sort of built this sort of framework or like a multi-level optimization approach that we can actually realize what should the design look like in order to achieve the kind of kinetic energy transfers that we would like to achieve. And then we did the experimental validation, and I mean, I was actually quite amazed by how, with all those similar sensitivities and challenges associated with the manufacturing of it, testing of it, and all of those, that you can see this in this graph E that I'm kind of circling round, that the red is the simulation and blue is the average experimental results, and it actually works really quite well as designed. So those are sort of two examples of how we're looking at multiphysics and multi-scale problems. I now want to move on and some of the methods that we were able to develop and use to solve a very like high number of elements style problem. So we did this some while ago. Essentially, we developed VDB, what we call LSTO. So VDB is a data structure and the level set method specifically designed to reduce the memory footprint of detailed geometry. This came out of the movie industry. So here is this example they published on this How to Train a Dragon. So essentially the idea is that in the level set method, because of the stability conditions, we don't make big changes. There's a CFD conditions where you don't really want to make big changes. All the changes are restricted within a narrow band where the interface is. So essentially, we don't actually need to do a lot of calculations outside a narrow band. So we only need sensitivities inside a narrow band. So as far as the level set method is concerned, we actually don't need level set grid anywhere other than at the interface. And that's really what this VDB is based upon. And then it did some clever things about mapping the data structures to the cache memory architecture in such a way that you can maximize the use of the data that we retrieve from RAM. So it has it has a number of advantages and things. So we then use this OpenVDB, which is an open source tailored for CPU, and then we applied it to our level set topology optimization. So here is just an example of the kind of thing. So here we're not doing any much changes to the FE solver. We're just changing the level set method, which is this advections bar graph. So the sort of traditional dense grid style approach obviously is the 40% of the overall time. So it was a reasonably significant component of one iteration of level set topology optimization, and it goes down to 4%. So we have an order of magnitude that we were able to gain. And now what we have as a result of it is that you can see all the red, which is the profiling for our level set, our topology optimization. By far the most is the PDE solve. So I think that's interesting to note that optimization actually doesn't take very long. It's actually PDE. So, and because we've reduced the memory footprint, we're able to run this 8 million elements on a 128 gigabyte RAM. So that's something that you can have on a engineering workstation. Here we parallelized it using PETSI, so we still have this problem with the final element being very slow, but in terms of all the other sections of it, we I think have a reasonably good compute efficiency. So now we are trying to apply this sparse grid idea to topology optimization and analysis of it. So this is one step that we have made. So this is a fluid optimization. So now essentially we don't need to do a lot of calculation inside the structure. So this is because what we're interested in is the shape in response to fluids. So what we have here is essentially we get rid of the mesh or the elements inside the solids. We replace them with just one row of solids and the boundary conditions, so that the flow sees sees the solids as boundary conditions. So now, in typical way that topology optimization generally deals with this kind of problem is to actually mesh the entire thing with the fluid equations with some what we call Brinkman penalization, which essentially works as 0-1 density variable. And so it actually solves for the entire elements, whereas this way we can only solve for the fluids and we don't have to keep the solids element. So we reduce the size of the problem. So here are some examples where we're saying so the Stokes-Brinkman, which is the standard topology optimization, and we're comparing that with our excluding solid sparse grid type approach. And you can see that memory usage is an order of magnitude smaller, and also as a result of it, and a few other things that we've done, CPU time is also an order of magnitude lower. So there's actually a lot of compute efficiencies in terms of orders of magnitude that we can gain by carefully thinking about what we're modeling and what we're solving for. So extending that to this two fluid heat exchanger problem. So we have a flow that's coming into these blue pipes from right to left, and then we have the hot fluids going from the bottom to top in this red through these red pipes. And we're doing a typical weighted optimization for heat exchanger, which is to consider the pressure drop of the fluids and the heat exchanged inside the heat exchanger domain. And when we did this work, this is our optimum design that we're getting. So you can see, I think what is probably interesting to note is how monotonic our optimization is. So it's very stable, it converges very well. We're seeing convergence after, I think here, we only sort of go to about 100, but you can see that it converges sort of, more or less well before that. It's 8 million elements. And again, we're running this on one processor. So we're not needing HPC, we're not needing all of this fancy computing. We can actually do quite a lot of computing on a workstation with a single processing unit. We're currently in the process of actually extending this to GPU, and we're sort of introducing new preconditioner and a few other tricks to be able to make this go faster. And we currently I haven't put those results in here, but we have another order of magnitude that we have reduced. So and here we're using a single GPU, which could it's the kind of thing that would be available on your sort of good spec laptop. So these are the kind of sort of large scale problem that you can actually solve in your everyday engineering computers. And we've done some verifications, doing the console calculations to compare that these these results are valid. So I talked a little bit about how we are going large scale and how we are focusing on reducing the compute densities by being careful about what we model and what we don't model. And I'm now going to move on to the last category of the large scale problem where we have the middle loop. So here, the reason why robust topology optimization or any kind of topology optimization with uncertainty is considered difficult is that most of the UQ techniques work when you have small design variables, and by that I mean like hundreds. That will be a tiny problem for us in topology optimization. We could not possibly imagine that 100 elements, 100 variables would actually give any kind of mechanical results to be reliable. So here is a typical robust optimization formulation where we are minimizing the objective functions expected value, and we are needing to also minimize the expected the objective functions variance or standard deviation. So these are the two things, which means that now we need to be able to compute this expected value and the variance values. Now, there has been a lot of work in the past where there has been various tricks to be able to calculate this without doing the general Monte Carlo, because general Monte Carlo is considered to be prohibitive. So a lot of research had focused on that. But the challenge with that is that every time we have some kind of uncertainties, we have to develop the methods and the way that we formulate it specifically to be able to deal with that particular uncertainties. And obviously those take multiple PhDs, and it doesn't really work within the sort of fast advancing technology era that we live in. So what we did was to work with people at Odin who had developed this multi-fidelity Monte Carlo technique, and we integrated that in the context of topology optimization. So rather than doing the high fidelity, so this is the inner loop where we're doing the high fidelity, sorry, this is the simulation loop where we're doing the high fidelity solve at every iterations. We now have multi-fidelity model, and basically the fundamental idea with multi-fidelity Monte Carlo is that there is some sort of optimum balance of number of samplings that's going to give you a better results versus the high fidelity results that's going to give you better results. Obviously, even if the fidelity is lower, if you can do more uncertainties sampling, then you could get better results. So recognizing that itself is an optimization problem, essentially this multi-fidelity Monte Carlo technique solves an inner optimization problem to determine that given the compute budget, what is the optimum use of different number of samples in different fidelity models, and it chooses where it's going to do the calculations and what method it was going to use to do what sampling. So we put it together to do topology optimization. I'm just going to give you some results as to what we are currently seeing. So we have a multi-fidelity, robust topology optimization, and this is an example that's reasonably well known in this context where we have just the rectangular domain, we have a vertical force, and if we do deterministic design, we get a vertical design. But obviously, if there's any imperfections or any uncertainties, that will topple over. That's an unstable design. So that's not what we'd like. We want something like this sort of a ladder-like design. And that's what all engineers would do. And this example that was done many years ago using a method that we developed to be able to solve that the probabilistic function, integral function that it was that could be solved without doing Monte Carlo. And these are the designs we got. So what we did was to then sort of divide these two things to say Z1 has one type of material, Z2 has two second types of material. Both of them have the same mean value, but the variance of your stiffness is very different. So when we do that, I'm just going to draw your attention to this design down here, optimized structure. We get the ladder-like thing, but depending on the variance that you get a sort of a different angles of that ladder, and that there is an additional horizontal sort of a strut that links the two to give this additional stability. So this is a reasonable optimum, knowing that this is the optimum design when Z1 and Z2 are both exactly the same material. So we were happy that this was essentially, we were happy that it was optimizing and giving us a solution that's more stable. I think what's really interesting is to note this graph on the right-hand side. So we use 5 fidelity models. So these are the 5 finite element models that we actually use. So M1 is what I considered the high fidelity, and M5 is the lowest fidelity. So topology optimization during topology optimization, we have these five different mesh density examples. You can see that really mesh 345 is far from the kinds of meshes that we would ever think about using to do the finite element analysis. But what you're seeing here is that the number of samples that it's used the most, the number of calculations that it's done the most, is actually this M4. So it does a lot of calculation in this M4 to the compute the Monte Carlo sampling. And then we actually know some things about how this model coarse mesh actually correlates to the high fidelity mesh. So we understand the effect of this low sampling because we also do some high fidelity, which is very small number of sampling. This is the red crosses that you see that essentially is very few. Even mesh 2 is actually quite low. And I think mesh 1 or 2 is what one might consider possible to use. And it actually uses mesh 3 and 4 mostly to do the Monte Carlo sampling. And at the beginning, when it's far from the optimum, even mesh 5, which looks like nothing really to us, actually gets used to do this sampling. So we get the same design as if we did the highest fidelity all the time. But obviously, we get at least an order of magnitude improvement in terms of the kinds of things that we can get. These are some of the research that I wanted to introduce in where we're going with large scale. So just to sort of summarize, I gave you multi-physics and multi-scale problems. I showed you a little bit about sparse grading approach and how we can actually manage large number of elements. And also we talked about topology optimization under uncertainties, taking more generic Monte Carlo style approach and still be able to get optimization results from our topology optimization. And I think this is really important to note that a lot of topology optimization for single linear physics, a lot of experts already have that kind of expertise, and we don't necessarily need topology optimization. It's somewhat intuitive if you gain that expertise. So the argument that you can make as to where topology optimization could be useful is that when you don't have a trained person in that area without expertise, and they can cleverly use topology optimization to get a design. Now, the challenge with that is that they then need to know how to use topology optimization really well. And in our experience, without any expertise, it is still difficult to get topology optimization to be set up correctly to give you a reasonable results. So it's not so reliable without expertise. But where topology optimization can become really useful are these sort of large scale problem with the levels of complexities that one engineer is not expected to have. So there's coupling complexities, coupling between scales, coupling between physics. If you have really large optimization, the results usually quite, kind of come out to be quite organic, very different from the way that we are trained to think. Under uncertainties, obviously, we don't really have an intuitions as to what they should look like. So when we have a real complex, unintuitive design space, this is where topology optimization can really help sort of accelerate our design. And it's this very complex, unintuitive design space that large-scale topology optimization represents. So with that, I just note that we have these lovely people that actually did all the work that was presented here. Thank you very much. I'm happy to take questions.
So thank you very much, Alicia. It was very interesting talk. Appreciate. So for the question, please feel free to use the chat feature or unmute yourself and ask your question. So already we have, I see that several questions in the chat. first question is a great presentation. Do you need to consider the difference between the epistemic uncertainty of reduced order models at different fidelities?
No, because we are just using simple Monte Carlo at the levels where we're sampling.
Okay.
It's
So
just that we're just deciding how many to sample from which model, and then using the correlation to compute the expected invariance values and their sensitivities.
okay, thank you. And then if you have a follow-up question, please unmute and follow up with your question if you have.
I don't have any. Thank you.
So, okay, so thank you. And Probin asking, thank you so much, Professor Kim. I had a few questions regarding the fluid topology optimization. First one is asking, how much of a seepage of fluid through solid domain, also with the boundary only solid version, is observed when running Stokes Brinkman simulation?
I think I can safely say virtually none, because we don't actually. First of all, there is one solid version, so there is, but we did the validation to show that this is very, very small, and then there is no fluids to be seepaged inside to the solid, so that doesn't really happen. The pressure drop difference, how much was it? Really good question. If I didn't write it, that probably means I don't know.
And the second question, Professor Kim trying to answer is how much of the pressure drop difference is observed when comparing the optimized model with the body fitted mesh? Yes.
Let's sort of see, because there is the hang on, let me move things around. Okay, so you can see from this graph, it's an order of magnitude, but the numbers obviously hard to read off from the logarithmic. I can send you the numbers. I think we have a paper on this. Pimanov et al. This is a collaboration that we did with Boeing, and this is the paper. So I'm going to have to refer you to go to that paper for specific numbers that we were getting.
Okay. And for calculating pressure drop, Alicia, do you do any reduced order model, or it is coming directly from Navier-Stokes? That's okay.
We actually did Stokes flow for this one. We're sort of developing extending it to Navier-Stokes now. Yeah, but no, we just calculate it from Stokes flow.
Okay. Regarding this fluid optimization, actually, I have two questions. One is the place that you are removing all of the solid. How you are deciding about the boundary conditions? I saw that when you are removing, you are putting a boundary condition inside of the one interface, a narrow interface. Is this a particular boundary condition, or it is just you are assuming it is fixed boundary condition?
So it's a no slip boundary condition. Sorry, I didn't say that.
Okay.
Right. Yeah. So we applied the no slip boundary conditions.
Okay. Yes. And you said that you have a huge, actually, I forgot the numbers, actually decrease in the amount of the CPU and RAM. This was because of the removing that solid part that you don't need necessary calculation?
Right. So essentially, in your matrix, we don't have all of these solid elements. So your system matrix is much smaller.
Okay. And any other question from the audience? Please,
one of the things that we actually also did was to develop a geometric multigrid solver. So in that case, I think the solids are back in because the structure doesn't change, but we actually are showing an order of magnitude there as well. So there is so many places. So in that solver, we do the matrix free. So the scaling is linear and it behaves really well. So that depending on the size of problem that you're solving and what you want to do, there are different approaches that we're investigating.
Okay. I have actually another question. If no one has any question, I can go ahead. Oh, there is a new question coming. In the nonlinear metametrial case, What is objective force intrusion curve? It is a question. What are the design variables, and what about scalability of the method in terms of computational cost?
So, so there are two optimization. So the first is happening at the discrete element, and here the optimization variable is the stiffness distribution. So we actually use third order function to approximate, well, to model the stiffness function. So C2, C3, these are the coefficients. That's what we're optimizing for at the discrete level. So then what we get as the output is this kind of nonlinear curve, like this blue curve is what we get out of sort of the first level optimization. Then we do topology optimization. So here is topology that we get. So level set, parameterization. So the design variables here is how, like, well, the way that we formulate our problem is that the design variables are essentially your velocities of the advection equation that we solve for the level set method, which then essentially changes the boundaries or interface. So that's our standard level set topology optimization formulation. So that's our design variable. And what are the other questions? Scalability of this problem. That's some so at the moment we've only looked at 2D design, mainly because experimentally 2D is just easier to do and it shows all the necessary ingredients. So and a lot of the studies that's going on in this area is actually looking at 2D results. So and the scalability, it really depends. And this is really the subject of the shape center that we have. There are so the studies that we did with Dreams project is that the nonlinearity was essentially snap through, bistability, that kind of thing, and that's what and geometric nonlinearity. Those are the two main nonlinear mechanisms that it uses at the lower scale to dissipate or absorb this kinetic energy. But if you actually, but in reality, there, depending on the material and depending on the impactor, there are different mechanisms like fracture, contact, and different types of nonlinearities can actually also be critical in being able to model the kinetic energy dissipation. So the scaling is hard to say because depending on which kind of nonlinearity is dominant and need to be modeled, that scaling behavior will change quite dramatically. So what we so again, like we're going back to the optimization part of it. If we're doing sparse grid, then obviously it goes in the order of squared. But if you are doing the if you're doing the FE, that the actual physics solver to do all these nonlinearities, that could take forever. So there are studies that actually try to model this kind of thing that I showed you. I mean, obviously, this isn't something that they would model. They would model something that actually stays stays in the boundary conditions. But essentially this sort of thing, what people are doing is to do finite element abacus with all nonlinearities in it, running at like, I'm going to make up a number, like 1 nanosecond time steps. With all nonlinearities turned on and doing explicit. And this one simulation could take, a week or more to do that. So those problems are currently not scalable because the analysis takes too long. So these are some of the things that we are studying.
Could you go, Alicia, in the previous slide, in the discrete one, so you are doing the optimization objective is you said that a stiffness distribution. What was the design parameter, the distance between them, or what is in the discrete one? What is the design parameter there?
The one I'm showing you is these design parameters is C2 and C3, which is the second and third coefficient
Okay.
of the polynomial description of this curve.
Okay.
We also
And
studied the length of A and effects of this and whatever else
okay.
you know, but I'm showing you the one that we did the
Okay.
yeah.
And then that is the input for your topology up level set topology optimization as the response of your one of those unit cells. Yes, that is the
That's the
uh,
target, right? That becomes the objective function.
okay. And I see that here your target, it is the black one in the B, and then in the right one you are up fitting to that. So it looks you have this target, it is a part of your design space. I mean, with your parameter, you can achieve that. Is there any case that your optimizer cannot duplicate this desired response, but get something close to that?
Yes, all the time.
Okay.
Yes, yes. And in this particular example, if it is sort of like something close but not quite, the behavior of these springs actually change completely.
Okay.
So in order to be able to sort of realize it in practice, this actually needs to match like 1% or less.
Okay.
So essentially what we consider for this example, if it gets close but not quite, we would consider that as a failure. Because for this particular application, that's not working. And we
Mhm.
are working on making this more reliable or robust. But I mean, I think the challenge here, and it is something that we're still studying, is this sort of behavior of convergence. There are nonlinear curves that are simply not achievable. And so we are doing studies to identify what is actually achievable limits. And we are like, trying to give that as constraints and things and, build up this design workflow to be more robust with the more knowledge that we can build in.
Okay, thank you. Any other question from the audience? I have several other, but I can't find Alicia again, but this is we have a few minutes. So, there is two question. In
Mhm.
your so it says in your chart you had M1, M5 scales. How do you decide that how many scale model need in a real application? I believe it is about the multi-fidelity one, probably.
Yes, that's right. And basically, that's what multi-fidelity Monte Carlo calculation is doing. So whether it's real or fake or whatever it might be, essentially we formulate the different finite element fidelities with different coarse level meshes, and that's automatically done. And you can change the parameters to control the range of fidelities that you want to do. And then you can also, so when it goes to do the sensitivity calculation in this blue box, what it does is that using the correlation coefficients of that design and knowing what is the sort of ground truth as the highest fidelity model, it will do initial optimization to work out how many samples you're going to get from which fidelity model to get the same level of accuracy, but do it much faster given the computational budget. So it actually solves that problem, and then it goes in and does all the calculations. So it's already done for you.
So deciding which fidelity actually has to be used in one of these optimization loop, it is automatic. So my
Yes, it's yeah.
okay. Okay. So there is one question from Probin. So he's asking, do you need remeshing the entire model when running the fluid topology optimization?
No. We're basically, I think I personally, not to say anything about like, what is good or not, but I personally just don't have the complex 3D meshing expertise. And I've seen how other people do things, and it's been difficult, and it takes a really long time when you have a 3D mesh that you are remeshing for fluids all the time, and same goes for structures. So we go with approaches where things are like regular. So here you just got a uniform mesh, and again, here we just got a background mesh that's Eulerian. If and when remeshing is somebody that knows a lot about remeshing really, wants to come in, then we can just change this method out and create a mapping function that links between the analysis, like unstructured mesh, to this, if that's easy to do, so that will be something that could be possible. I mean, there is the question of, is that possible? Is that worth doing this mapping when you have unstructured mesh? How long does that take? I think there's a lot of questions that arise from it. It's just that personally, I just don't have that level of expertise in remeshing, so or mesh generation. So we're sticking with regular mesh.
Okay, just one question. Since you are using level set at the end, are you for your analysis using the projection on the regular finite element or XFEM or kind of the cutted fit element?
You could do anything, really. So level set grid is just used for level set propagation.
For design.
It's not used for the PDE soul. So here we're using particle methods. You could use XFEM. Yeah, you can use like whatever you want.
Okay, so good. So really appreciate, Alicia. Is there any other question? So I see Sachi asking, am I correct that here you have used mesh refinement as fidelity and only one single response you are predicting? In usual cases, the fidelity reflects how models fidelity to replicate geometry, loads, and boundary condition physics, and the discretization. Often this means the different model have different level of accuracy in prediction, different response. What challenges do you see in extending the multi-fidelity framework here to such problem? Because you have different accuracy.
Sure. So this multi-fidelity Monte Carlo technique actually has been used for a whole variety of problems, including some of the fidelity being experimental results or some data-driven method. So we don't think that the generality of this MFMC doesn't limit the sort of, whatever it is, right? But essentially, to do topology optimization, we need the field values. So that's the sensitivities that we need. So it basically is whatever the fidelity model that you want to introduce, can we calculate the sensitivities? And if that's possible, then we believe that it should be usable, and we're not expecting from the MFMC perspective that there would be any challenges, just because they've already done a lot of applications with lots of different things. I think what we're doing is applying a reasonably generalized method in the context of topology optimization, so we can solve topology optimization for general uncertainties.
So with this question, I will end this presentation. Really lovely presentation and talks. And thank you, Alicia, for accepting our invitation and giving us about 15-20 minutes to ask many, many questions. And if audience, they have more questions, you can reach to Professor Kim directly. And for audience, again, be tuned. We will announce the next speaker very soon for the rest of the winter and spring terms. So thank you very much from everyone. Appreciate.